This is the third video explaining these slides about relations. In these slides, we will speak about the inverse of a relation. For the definition, assume that R is a relation from a set A to a set B. Then the inverse of R is also a relation from the set B to the set A, and it will be denoted by R inverse. So here is the relation R, and the inverse will be R to the power minus 1. We mean the inverse relation. And you take all the pairs y and x such that x and y is in the original relation. Note that since x and y is in R, that means y is an element in B, while x is an element in A. So R inverse is a relation from B, the set B, to the set A. Let us illustrate the definition in this example. So I am taking the set A to be the set which contains 4 elements, minus 1, 2, 3, and 4. And B is the set contains 5 elements, 1, 2, 4, 5, and 6. And we take the relation R, which contains 4 elements. Here the pairs minus 1, 5, 2 and 4, 2 and 1, and 4 and 2. This is a relation from A to B. So the inverse of this relation will be denoted by R inverse. I just swap the first coordinate with the second coordinate. So here we have minus 1, 5. In R inverse it will be 5 and minus 1. And similarly, we will get 4 and 2, 1, 2, and 2, 4. Note that if this is a row diagram for my relation R, then the row diagram of my relation, the inverse relation, will be simply by flipping all this diagram with the arrows. So the arrow diagram for the inverse relation will be like this one. So I put B and A and just flip the arrows. The discussion we have about the arrow diagram for a relation R and of its inverse leads to this theorem. This theorem says that let R be a relation from A to B, then the domain of the inverse relation is equal to the range of the original relation, and the domain of the original relation is equal to the range of the inverse relation. For the proof, I will just discuss the proof of A, the domain of the inverse relation is equal to the range of the relation R, and I use a biconditional proof. So note that if we take X an element in the set B, then X is an element in the domain of the inverse relation, and the inverse relation is a relation from B to A, if and only if we can find Y in the set A such that X, which is in B, and Y, which is in A, in the inverse relation. And this happens if and only if we can find this Y in A such that when we flip this one, it will be YX, it will be in the relation R. So notice that XY in the inverse relation by definition if and only if YX in the relation R. And what that means? It means that since we have here X appears on the second coordinate of the relation R, that means X in the range. And the other way around, if we have X in the range, we can conclude that X will be in the domain of R inverse. What that means? It means that this subset domain of relation R inverse is a subset of the range, and also the range of R is a subset of the domain of the inverse of R. And that means two sets are equal. We had an example before about how to find the inverse relation when the relation is finite. And in this example, I will give you a relation which is infinite. The elements of this relation is infinite. And we will try to find the inverse of this relation. So in this example, let S be a relation from R to R defined by all the pairs x, y, where is the second coordinate, here is y, is less than the first coordinate square minus 8. So the question here, find S inverse, the inverse of this relation, and write it as a set of pairs x, y, subject to some reconditions. So for this type of examples, we need only just to use the definition. So what we have as a definition? We have the pairs x and y belong to the inverse of my relation, if and only if yx in the relation, and yx in the relation if the second coordinates where here is x is less than the first coordinate where here is y squared minus 8. And this happens if and only if this inequality I have x plus 8 is less than y squared. And this inequality happens if and only if y is less than the minus square root of x plus 8, or y is greater than the square root of x plus 8. And this gives me a condition. So xy belong to the inverse of my relation S, if and only if these conditions happens. That means I can define my relation S inverse as all the set of x and y, the pairs x and y, such that y is less than minus square root of x plus 8, or y is greater than square root of x plus 8. And this is what we want to discuss in the third part about the inverse of a relation. Next, we will speak about composition of relations.